Log on, tune in, find out. Another good idea from Cambridge.
And I would like to remind you that please check these practical reminders of the Institute before you check out. But before that, we are now going to continue Samuli Siltanen's lecture. Please.
Thank you. So today I will be talking about this X-ray tomography problem in more detail. I will show you some computational approaches to solving the problem in a regularized way. I will be talking truncated singular value decomposition, Tikhonov regularization, and total variation regularization. So 3 techniques. But let's recall what is our measurement. So the measurement equation we use is this one. Here M is a vector in Rk. We are dealing with only discretized problems because we are working with a computer, so everything needs to be finite. So actually F I consider here to be a vector in Rn. Epsilon is also a vector in Rk. It's random measurement noise, and in the MATLAB simulations I will be showing you, I will simulate this as using the command rund_n with some amplitude, I don't know, noise level C. This rund_n gives a vector with components independently distributed randomly according to the normal distribution. So we'll take just a realization of such a random number and add it here when simulating the data. Now, of course, matrix A, because it's multiplying an n vector, it must have n columns and k rows. So the number of rows, the number of columns. I use the same ordering in these indices than in MATLAB. And what are these guys? When simulating data, I'm using the so-called Shep-Logan phantom, which is in MATLAB a ready-made function. And the Shep-Logan phantom is kind of a simulated cross-section of a human head. So it has some kind of ellipses inside with different outside it's 0 attenuation, and inside is something, and there's also a skull layer around here. The phantom is defined by ellipses, so it's defined in a kind of with infinite accuracy, and it can be realized with any resolution. So what happens, F has to be a vector in Rn. So actually what happens is that we pixelize this image with, let's say, n times n pixels, meaning that n is n squared, so the dimension of this F is the number of pixels here. And although this is an image, let me stress that we number the pixels in this way, so then we treat it as a vector. But of course, we should think of it as a 2-dimensional pixel image. And then the data, M, what is this matrix A? Well, the day before yesterday, we looked a little bit in a simple example how to construct A. And in MATLAB, I used the command radon.m. It will use parallel beam geometry, so it will compute. We can choose the angles of imaging. So we take X-ray images in different angles, and we organize those. So every projection image is just a 1-dimensional vector. And we organize, when viewing the data, we organize it in this sinogram form. So let's say first we take a vertical picture, so just a vertical line integrals through this piecewise constant function, and the resulting vector we put here. Then we turn a little bit and take another picture from another direction and put it here, and then another direction here, and so on, and we collect it like this, and again we number the pixels in this way, and finally here is pixel number k. So this is the dimension of the data. So there's a little bit of confusion maybe between two-dimensional pixel images and vectors, because these guys here are vectors. But it's just that we number the pixels in these images in such a fashion, and then we treat them as vectors, and A is just a matrix or linear operator between these vectors. But when I show you the vectors f and m, I will show them as pictures like this. It is more convenient to our eyes to view them in that way. And MATLAB's Radon gives us, if we give it such an image and a number of imaging angles, it will automatically compute for us this sinogram, and it will actually automatically choose the number of pixels in this row in a kind of not so clear fashion, but we don't need to care, we let MATLAB take care of that. So that's the way I will simulate data for you. And when avoiding inverse crime, we shouldn't simulate the data with some matrix A or with the Radon command with one resolution and then use the same resolution in the inversion. Then we will get unrealistically good reconstructions like I showed you the day before, and I will quickly show today again. So what I do in this case is that when simulating the data, I will take double resolution in the phantom, use the same imaging angles when creating the data, and then interpolating the data, not interpolating, but kind of downsampling the data to a smaller resolution. It's not a perfect way to avoid inverse crime, but it seems to be a sufficient way, at least for the purposes of the demonstration. And one more note, let me still mention that at some point we will be needing the transpose of the A matrix, and that is actually the so-called back projection. And let's say we have here our object of imaging, so we are taking X-rays in many directions. So this is the what the matrix A is doing. It's computing line integrals along these lines. But what is A transpose doing? Of course, the A transpose, so A maps from n vectors like f to k vectors like m. The transpose does the opposite. It multiplies k vectors and produces n vectors. And what happens with back projection is that, so the end result of the back projection is an n by n image, like f. And how is it constructed given some sinogram? The idea is, let's say in this point, what would be the value, the result of the A transpose? The idea is to take all data measured along X-rays that go through this point and take data points related to each of these X-rays and then just add all of the data and attach that number to this point. This is the back projection. So projection and back projection, A and A transpose, and actually in MATLAB the action of this guy can be computed by iRadon.m command, which is the inverse of Radon. But if you choose here to use as filter, you choose none, so no filter, then it actually will be the back projection operator. And that will actually later allow us to work with very high dimensional problems in a matrix-free way, so that we will not actually construct these matrices A and A transpose in the computer memory, because with big problems that takes a lot of space, actually too much. So what we can do is to devise our inversion method so that we never actually need those matrices. We only need to be able to multiply a given vector with that matrix. Such a multiplication we can actually implement by the Radon command and iRadon command without ever constructing the matrices. This is of utmost importance in practical problems of high dimension, to use such matrix-free iterative methods. Okay, so here is the basic framework, and let's move on to our first regularized inversion method. Namely, as we saw the so-called, what I call naive inversion. Naive inversion would be to take the inverse of A or maybe the pseudo inverse of A if it's not square and apply it to data. And as we saw, and we'll see today again, this does not work for ill-posed problems. If the matrix A comes from an ill-posed problem, such a simple approach will just fail. It doesn't work. We need something regularized. And as a first regularized method, let's study truncated singular value decomposition. Truncated singular value decomposition. And I will call this singular value decomposition as SVD in short in what follows. So, singular value decomposition, what is it? Many of you probably have heard about it. I will not go into the construction in the interest of time, but I will give you the crucial properties of this decomposition. Namely, we write the matrix A, and now it's any matrix. It doesn't have to be square or anything. This works for any given matrix. We write it in this form. We have a U, then a diagonal matrix D, in a sense I will explain in a minute, and V transpose. This is the decomposition, and the crucial properties of these guys is that, of course, first of all, U is a K by K matrix, V is an N by N matrix, and they are orthogonal matrices. U transpose times U is the identity matrix, and also the other way around. So the inverse is given by the transpose. It's an orthogonal matrix, and the same goes with this V guy. So there's such a property. So it's just a coordinate transformation, orthogonal coordinate, kind of a rotation. And D matrix, which has the same size than A, K times N, is diagonal. Well, what does it mean for a matrix D to be diagonal if it is not square? Let me just point out the various possibilities here, because K and N might be equal, or one of them might be bigger than the other. So we have this kind of possibilities. Maybe U is such a small matrix, and D is kind of a long matrix like this, and so this is one possibility. In this case, in D, all other elements are 0 except those that have the same row and column index. So these guys here may be different from 0. Then there is another possibility. Of course, there's the nice possibility that everything is just square. Then it's just the usual way, diagonal matrix. And of course, it can be that U is bigger than V. In that case, we have this kind of shape of matrices. And in this case, again, just the elements that have the same row and column index can differ from 0. But they do not necessarily differ from 0. The diagonal elements of D are called the singular values, and they are the key to studying if a given matrix A describes an ill-posed problem or not. Actually, these singular values tell everything we need to know about the matrix A. And these are the singular values of A, and they are non-negative numbers. the diagonal elements, and I number them just from 1, 2, 3, 4 up to the minimum of k and n. And they are actually automatically ordered from the largest to the smallest. Here is the last one. This index is the minimum of k and n, and they are all greater or equal to 0. Of course, they may all be 0 if A to begin with is the 0 matrix. Then these are all 0. But in practical inverse problems, what usually happens is that some of the last ones may be 0, and the singular values kind of gradually decrease in size to go close to 0. We'll see soon for some examples with the X-ray matrix how these singular values look like. But let me draw you a picture how we can check the Adamard's conditions of an ill-posed problem in the case that we know the singular values of A. So the matrix A maps from Rn to Rk by vector multiplication, and let me just schematically denote this Rn with this kind of a picture. Now every interval like this here denotes one dimension, so actually my Rn is 1, 2, 3, 4, 5, 6 is R6 actually just in this example. And let me write this, let's have maybe a bit less dimensions here. Of course there may be, no, that's the same number. Let me try to correct. Corrected. Okay, so now how does a matrix map between Euclidean spaces? Well, some of the dimensions may be mapped in a bijective fashion. Then there also might be some kernel involved. This will be the dimensions that the matrix will map to 0, these guys. And then there is also some part of the target space that no vector here will be mapped into. This is the so-called co-kernel of A. And this is the range space of A. These are all linear subspaces of the Euclidean spaces in question. And so this part here is kind of mapped into nothing. This is just mapped to 0. So now what we need in an inverse problem, we are given an element in this data space, and we would need to find what was the f here that produced the data. And now we can analyze what happens with Adamard's conditions. If there is some kernel here, then Adamard's condition, this is condition number 2, uniqueness, will fail. If there is some kernel, then we can always add an element of the kernel to our reconstruction, and it will map to the same data because the addition from the kernel will map to 0 and have no effect. On the other hand, our data, if there is such a co-kernel, then our data might be picked from this part of the space. So if our M is picked from this part, then there is no element in Rn that would get mapped here. So then we have a problem with Adamard's condition number 1, existence. There is no f giving such data. And then how to analyze the continuity of Adamard's, the condition number 3, that the output of the process, of the reconstruction process, should depend continuously on the data. Well, in this finite dimensional situation, we cannot really, strictly speaking, see it, because let's say if we have this situation with the square matrix, just for the sake of the argument, let's say if all of the singular values are positive and k equals n, in this case we can write A inverse is V D inverse U transpose, which I will write explicitly like this. We take 1 over d1, 1 over d2, and so on, 1 over dn, like this, and here we have. So strictly mathematically speaking, in this case, we can just invert the matrix. But the way to detect the third condition of Hadamard using singular values is just to plot the singular values, and if we are dealing with an ill-posed problem, the singular values kind of gradually go to 0 like this. If it's just a rank deficient problem, then it would look something like this. There are some non-zero singular values, and then suddenly they just drop to 0 and all the rest are 0. Then it's just a matter of having a kernel and maybe working with some quotient spaces. But with true ill-posed problems, this is what happens. We have the singular values gradually going towards 0, so the last one is many orders of magnitude smaller than the first one. So still, we can, strictly speaking, mathematically speaking, we can write this, we can invert the matrix, but what happens is that this guy is huge. This is some reasonable size number here, but because dn, the last one, is so small, this is so much bigger than this guy. And that's why there is a concept called the condition number of a matrix. Condition number of a matrix is defined in this way. And if this is big, then we are dealing with very unstable inversion, because any noise in the data will be multiplied by very large numbers due to this region. So strictly speaking, we cannot really detect Hadamard's condition number 3, the non-continuity of the process, because well, the matrix is invertible, and we should decide what is big enough condition number to be discontinuous. It's not rigorously defined. What we can do, though, is to look at the underlying continuous inverse problem with finer and finer discretizations to go towards the limit case when we have an operator and an infinite singular system where we have an infinite number of singular values, and then we can just define its ill-posed if the singular values go to 0 at the limit. But with the finite dimensional case, we cannot, rigorously speaking, do that. But we can, as we will see, it's really, actually in practice, it's really easy just to see, okay, it's an ill-posed problem. If you see this kind of behavior, then it's ill-posed. It's just, you know it when you see it, but it's hard to define rigorously. Okay. And now the truncated SVD. How does it work? In truncated SVD, the idea is to do almost this, but avoid these big numbers by just replacing these guys by 0. Only use these guys up to some point, and then the rest of the diagonal elements we just take to be 0. That's the trick. So I define a regularized inversion method. Now, actually, in this case, I will index it not by a regularization parameter, which is a positive real number, but actually with, n is unfortunate, let's put m. But with an index m, where to cut the expansion. So, how to compute the reconstruction is to kind of use this formula, but instead of this very unstable guy, we just only have these up to this point, up to some index m, we use the actual inverses, and from that point on, we just use 0. And of course everything else is 0 in this diagonal matrix. And here we have U transpose multiplying M. So this is our first example of some regularized inversion method. We can choose the number of singular values and vectors to use. There are also automatic methods. Of course, we should algorithmically choose this one based on the noise level. I will not go into more details with those methods. There are many suggested methods in the literature for that. But I will just make a note about the structure of the solution we get this way. Because notice, this is just a vector in Rk, then it's multiplied by k matrix, so also this here is just a vector in Rk. Then we multiply it by a diagonal matrix, so again the result is just a matrix in Rk. So let me write this. We see that this is actually the matrix V multiplying some vector B. B is in Rk. So now we can, if I call the columns of this matrix by V1, V2, and so on, by simple matrix algebra, we see that this matrix vector multiplication can be written in this form. First element of this guy times the first column of V, plus second element times the second column, and so on until, oh sorry, this is of course a n, sorry, in Rn of course. So we see that, and actually we have only up to m. Okay, we have here, of course, but it's only up to m because the rest are 0, so this is just up to m, like this. So the structure of the reconstruction we get, it's a linear combination of the m first columns of the matrix V. So the columns of the matrix V are kind of the building blocks of our reconstruction. It's good in a way that we can understand by looking at the singular vectors, we can see what kind of building blocks we are using. That's a good side. The downside is that it's kind of restricted because we only can get reconstructions that are of this form. So that's kind of a drawback of this method. But let's see how these reconstructions look like in our X-ray example. And let me note that in the examples I will be showing you, I choose 3 different resolutions here. I will be using n equals 16, 32, and 50. There's no deep reason behind these numbers. They are just a result of some experimenting and seeing how can I get some nice examples. But let's just, because it's nice to see these things at different resolutions, so we'll use these ones. And let me note that in these examples, I will always use exactly n directions of X-ray imaging. They are equally distributed angles around the full angle, and the number of imaging angles is the same than n. There's also no deep reason behind that. It's just kind of convenient to have the number of directions growing with the resolution. So let's see, for example, when n is 50, then f belongs to R 2500. So if n is 50, then n is this, and k equals, well, we have 50 angles, and then as I said, the MATLAB will produce automatically some number of these X-rays. It's not the same as n, because in the diagonal way there's a different number, because actually the deviation between the rays is the same as the pixels. So there will be some number of rays I will call, let's say k, we'll see. But the size, this is more than 50 anyway, so the matrix A will have 200, 500 columns and more than that rows. So it's already a bit substantial matrix. And I have pre-constructed those matrices for you using the radon command, and in kind of a cumbersome way, just to compute the elements of that matrix and then define it as a sparse matrix in MATLAB, so that only the non-zero values of the matrix are stored to kind of keep the memory requirements lower. But let's go into the example now. Okay. So I have put all of these MATLAB files for you to test. They will appear on the course website today afternoon. So they will be in a big zip file, so you can download the zip file and use these, study these codes and modify them. If you want to use them in your research, I ask you please to refer to the origin of the files, but you can just go ahead and play around with them as much as you want. Okay, so it starts with this X-ray. M stands for matrix, because in these cases we use these explicitly constructed sparse matrices. And this guy here computes these matrices. So here we have, for various sizes, we have computed these matrices. And here we actually compute the data with no inverse crime. So let's go. So let's see this. Let's compute some naive reconstructions. Okay, so here we see this is the sinogram, this is the measurement 16 angles of our phantom. Oh, Steve, can I have this a bit lower, please? I think it's not all. And well, here is the naive reconstruction, but it's with inverse crime, so we get a perfect reconstruction. But immediately when we add just a little bit of noise into data, it blows up. We can do this again with higher resolution. Again, we see that oh, this is the sinogram now with inverse crime. This is the perfect reconstruction due to inverse crime, and this is the reconstruction if we have a very small amount of data. It blows up completely. And the same with the 50. It takes a minute. So here, with inverse crime, without inverse crime. Oh, not with inverse crime, but with noise. Okay, so then if we continue and simulate the data with no inverse crime anymore, and we again try the naive reconstruction. Well, the difference is just that now we get now even with naive reconstruction, so the inverse crime is gone now. Again, we get just rubbish, and this happens now with every resolution. And well, the result here is that after some work, we see that nothing works anymore. With inverse crime, we at least saw that something worked, but now nothing works anymore. Let me just show you also. This is how the matrix looks like. These are the non-zero elements of the matrix A, and it seems we have 2,500 columns and 3,750 rows. and here you can see the non-zero elements. So the matrix is kind of sparse, mostly zero elements. Okay, so the naive inversion doesn't work for an ill-posed problem. So let's go forward and compute the singular value decomposition of the matrices. I have pre-computed. It takes a while. It's kind of at least for the 50 times 50 case, it takes some while, so I don't do it here. I'll just show you the results. So here, let's start computing. Here you can see the singular vector number 1, marked by this red dot here. So this is the first building block, and the reconstruction with using only one vector looks pretty bad, and we have relative error 86, so there's not much right in that. So let's use some more. So this is the singular vector number 26, and this is the reconstruction using all singular vectors up to 26. And let's move forward. Now we use 51, so you can already see some kind of nice behavior here. Number 76. Yeah, maybe we see already something, maybe. And now you see the singular values. This is the sign of an ill-posed problem. Notice that this is in logarithmic scale. So these are many orders of magnitude here. And the singular values, first there are some useful ones, and then the size of the singular values just drops down, meaning that these are the useless and very non-stable, unstable ones. So let's see what happens when we move forward. So this is kind of not good, but at least something. But now that we start using these guys, you see, then that's when it breaks up. This is where the ill-posedness really makes the difference. So let's compute the same thing now with higher resolution. With 32. Okay, singular vector number 1, very low frequency. Singular vector number 103, you see some nice structure there. And now you start seeing the error is already only 64%, so it's lower, and we have still some useful singular values to use. So now this already kind of looks like the phantom already. Error is, well, 65 is kind of a biggish still. And now we're moving again to these parts of the small ones, and you see then it blows up. And let's see, do the highest example with 50. No, this one, this one. Okay. So it takes a while. So now we're using 250, about 500. So now the error is even only 51% relative error. But now it's starting to grow, and again we are going down this slippery slope to instability. And we see more and more problems coming up with using these very unstable singular values. So this is our method number 1. And then I think I have time to define Tikhonov regularization still within this lecture. Okay, so that was truncated SVD. And as I said, it's kind of limited in its use because it's always a linear combination of those same building blocks of the matrix V, and the matrix V is dictated by the matrix A. So everything kind of comes from the measurement matrix. But now we can follow the great master Tikhonov in defining another way of regularizing inverse problems. And here the idea is to minimize, find the vector that minimizes the following functional. So here we have AF. So this we take the minimization over vectors in Rn, and what we minimize is, given the data, we compute just the Euclidean norm of this difference between these guys, and this is the discrepancy or error. If we have any f, kind of a candidate, would this be a good reconstruction? We measure here how good measurements will it give. We compute kind of, so to say, simulated measurements from f using our measurement matrix. Then we compare it to the actual measurement m. And well, in view of the measurements, f is good if it gives as closely as possible the same measurements. But then, as we saw in the case of the limited angle tomography problem, there may be non-uniqueness in inverse problems. So there may be several f's that give exactly the same data. And then this is not really decisive just to find the minimum of this expression. So following a great intuition of Master Tikhonov, we add another requirement. We have some regularization parameter alpha, a positive number, and we require that f itself shouldn't be too large. So this is like a penalty functional. We are giving two kinds of penalty to f. We penalize f if it gives the wrong kind of measurements. Then this number will be big. And we penalize f for being too large. And we sum up these two penalties, and this guy gives kind of a balance between these requirements, which one we require more. And you can see that in the limit when, so here the regularization parameter alpha is a positive real number. So if this is 0, we are dealing only with the measurement data, and with ill-posed problems, this will not be good. There will be several f's, and we cannot really make a decision what's the right one. In the limit when alpha goes to infinity, then this guy loses its effect on the whole thing, and actually f equals 0 is what we get at that limit. And the best reconstruction is somewhere in between with some kind of finite size alpha. And actually the choice of the best or correct alpha is a really difficult problem. There have been several methods suggested for that, like Morozov's discrepancy principle and L-curve method, some cross-correlation methods, but I would say it's not fully settled how to choose alpha optimally in a general situation. So in my examples I will show in the next lecture, we will just choose some alphas and see how the reconstructions look like. So we will be minimizing this functional, and let me end this lecture by mentioning that there are several ways of computing the minimizer of this one. One way is to use the SVD. It's a quite explicit formula. That's not so good computational because SVD is expensive. Then it's possible to use optimization methods, but also it's possible to write this in so-called normal equations form, which we will see later today, and that can be solved actually with iterative methods without ever constructing the matrix A. And I will show you how to deal with really big dimension problems using that approach later today.